Glad you all could come. We're especially pleased to have our colleagues from a few different other disciplines here today. A while back, a thing happened that I want to tell you about because I wish it would happen more often. Salah Muhammad came to me, and he had been to a conference. And he said, I heard this really good talk. We should have her come here and give a colloquium talk. And now she is here. We're pleased to have with us Kirkpatrick from the University of Illinois in Urbana-Champaign. You can see her title. We look forward to hearing what you have to say.
Thank you, Wesley. Thank you for the invitation to come speak. I'm very happy to be here. It's my first time. And you'll be pleased to know that spring is here earlier than in Urbana. So I will be talking about some mean field models from physics that model superconductors and magnets. And so, just for fun, I have a picture of a superconductor here, my favorite superhero. And this is joint work with Elizabeth Meckes from Case Western. And I want to start with a story about Sophie Kovalevsky. So when she arrived in Berlin, she was not allowed to take classes at the university. And she wasn't even supposed to be able to meet Weierstrass. But she got past Weierstrass's maids at his house, and she got past his sisters, because he had sisters helping him keep the house. And so she got to meet Weierstrass. And part of the way she got past all of them is she disguised how young she was with this giant hat and this huge cloak. And so Weierstrass finally met her, and he had kind of the usual way of discouraging a prospective student. He gave her a list of problems to solve and 1 week to solve them in, and that if she solved all of them and came back and gave the solutions, that then he would talk with her some more. And she went away, and he promptly forgot about her. And of course, 1 week later, she shows up. He doesn't recognize her at first until she presents her solutions to him. But Weierstrass is still a bit skeptical, and he wonders if maybe a man helped solve the problems for her, perhaps a husband or a brother. And so he made her explain the solutions to him. And she did. And many of these solutions were original, and he thought brilliant. And he realized in that moment, and he told her this some years later, that he realized this was the student he had been waiting for his whole life. And she went on to write a thesis in mathematical physics, essentially, on a couple of different topics, including analysis of PDEs and an analysis of the range of Saturn. And she was, in a very real way, anticipating Hilbert's sixth problem, which is making physics rigorous. And that is my field, mathematical physics, trying to really make it rigorous from first principles, which are usually on a microscopic level. We set up some model that describes the microscopic particles, how they interact, and then there is usually some way of stepping back away from these particles or zooming out to end up with some sort of macroscopic description. So this is the overall scheme of my field of statistical mechanics. And here's an example by way of picture. So on the left here, you can think of these blue particles as water molecules, and the red ones as the dye, red dye in the water. And they're all bouncing around. If I had my computer, I would show you an animation of these bouncing around in a Newtonian fashion. And if you start with red dye at one particular point, then what you see on the macroscopic scale is a diffusion. And there's a long history of understanding how to get from these Newtonian interactions to the macroscopic diffusion, which is given by a heat equation. And one simplification is a simple random walk from which you can zoom out in the appropriate way, rescale it, and get a Brownian motion. And we know that Brownian motion is connected to the heat equation in a very precise way. So this is a picture of the kind of general idea of something I try to do in my work, going from some sort of microscopic model, zooming out in some appropriate way, and getting some sort of macroscopic description. And in particular, this talk is about the following microscopic and macroscopic stuff. For superconductors and magnets, we construct on the microscopic level what are called spin models. And each one of these arrows is a spin. In this case, this picture is like for an Ising model or an Ising model, spin up or spin down. And at low temperatures, the spins want to line up. At high temperatures, they can be anti-aligned, and there's not much penalty for that. And then, and this is not yet, the next slide will explain kind of the pieces of this that are already known. But overall, we don't really know how to go from these kinds of microscopic spin models to the macroscopic PDEs that describe magnetism and superconductivity. This is a big open problem. There is a huge puzzle, some pieces of which we have, most of which we don't. And to give you an idea of which pieces of this big puzzle that we have, well, superconductivity goes back to 1911. The physicist Onnes was trying to liquefy helium, and in the process of doing this, he was using mercury, and he was measuring the resistivity of mercury, and at one point, the resistivity of the mercury just went to 0. And that's not only perfect conductivity, but also exhibits features of superconductivity, which is more than just perfect conductivity. There are other features like the Meissner effect. And so that was the start of superconductivity. And then in the 60s, at Urbana-Champaign, in fact, it was conjectured what describes superconductivity, at least on a mesoscopic level. And it was also conjectured how you could go from this mesoscopic description of Harding, Cooper, and Schrieffer to the macroscopic equations, which are given by Ginsburg and Landau, and also Ginsburg-Landau is for the critical temperature. And Bose-Einstein condensation is the picture of superconductivity at 0 temperature. But all of these things back in the 60s were purely heuristic and not yet understood rigorously. And some aspects of this we are now starting to understand rigorously, and I've been part of this. For Bose-Einstein condensation, part of my postdoc work at MIT was at 0 temperature going from quantum systems to the BEC equation, which is a nonlinear Schrödinger equation. And then people I've worked with and others have also figured out how to go from the BCS theory to, well, at least the static Ginsburg-Landau equation. And so we have a few pieces of this puzzle, very few really, but the overall scheme is from these microscopic spin models, like Ising, with the arrows. It's thought that there's a way to get from there to the mesoscopic BCS theory, and then from this mesoscopic theory, we can, in some cases, get to macroscopic equations. But there's a lot to fill in, and in particular, the hardest part is going directly from the microscopic models to the macroscopic equations without going through this mesoscopic. So there's a lot left to figure out, and I'll be talking about some specific aspects of the microscopic models that have some macroscopic features that are really interesting, and that must be connected to the things with these macroscopic equations, but we don't yet understand. So this is kind of an overall picture of this part of the field. And just to raise the stakes a little bit, one of the applications of superconducting magnets is in the ring around an MRI machine. That is a superconducting magnet, and this is very useful in medicine. So if we could understand superconductors better, the hope could be that maybe we could make MRI machines less expensive, for instance. So this is a connection to the real world. the outline of the specific models I'll be talking about. First, I'll talk about the Ising model, which is the most fundamental model in this field and is fairly well understood. And then I'll mention a little bit about what's called the XY model at the end of the talk. This is where the spins are allowed to be in a circle instead of just up or down. And I'll spend most of the talk talking about the Heisenberg model, where the spins are allowed to be not just up or down or in a circle, but anywhere in a sphere. And these models actually have a coherent set of equations describing them that I'll get to later. And for instance, if we talk about the Ising model, this up or down spin model, this goes back to 1925. And so these spins, the arrows that I was talking about, are sigma I, and each one of the arrows is plus or minus 1. And so the vector sigma is a vector of these arrows, and the Hamiltonian energy, this is a fundamental object in statistical mechanics. The Hamiltonian energy is minus the sum of the products of neighboring spins. So you can see if neighboring spins are the same as each other, then you get a plus sign here, and if they're opposite, you get a negative sign. So you'll get the lowest energy if all the spins have the same value, either all plus or all minus. And the negative sign makes it so you want the energy to be as low as possible. And here's a picture of these two lowest energy states, all plus, so that all of the terms with the sum are plus 1, and all minus. And again, all the terms with the sum are plus 1. And these two states are very special. They're called ground states because they are the lowest energy states. And are global minima in the energy landscape for this function. This is a very high-dimensional function. There's a complicated energy landscape, but there are two global valleys, and these are those two valleys. Okay, so if we have this energy set up, you can think of this energy landscape. Well, how do you choose configurations, sigma, in a natural way that reflects the actual physics going on? So the intuition is that the lower the temperature is, the more you want to see the ground states, the lowest energy states. And then the higher the temperature is, the more freedom you have in some sense, and spins can be anti-aligned. And higher temperature, you may know, like if you take a magnet and heat it up, it demagnetizes, because then the arrows don't have to be, the spins don't have to be lined up. So the way that we capture this in statistical mechanics, and this is an idea sort of coming from probability, is through the Gibbs measures. And the Gibbs measures, the Z inverse is just a normalizing constant. In physics, it's called the partition function. And you take e to the minus beta h of sigma. And beta is the inverse temperature. So 1 over kb times T. T is the temperature and kb is the Boltzmann constant. And so in terms of our Hamiltonian that I wrote on the previous slide, this is z inverse times e to the beta sum of the sigma I times sigma I plus 1. And so the idea is that this measure is a probability measure that we put on the space of all configurations, and it tells us which configurations we're more likely to see. Now, of course, which configurations we're more likely to see should depend on the temperature, should depend on beta. And the next key idea is how we look for this dependence on the temperature. So in the high temperature case, this is beta equals 0. Then if you look at e to the minus 0, well, that's just the uniform measure. So you're equally likely to see any configuration. And what that means is since you're equally likely to see any configuration, the spins are actually independent of each other. Because the uniform measure is actually a product measure on this product space. So the spins are independent at, and this is actually infinite temperature, when beta equals 0. And then on the other hand, at low temperature, this corresponds to beta equals infinity. Well, if you roughly think of e to the minus infinity times the energy, this is going to favor heavily the lowest energy states. There's going to be some mass of the probability at the lowest energy states, and then there's going to be basically no mass of the probability measure at any of the higher energy states because the decay is so fast in this exponential. And because it favors the lowest energy states, this measure concentrates on the ground states. Whenever beta is close to infinity, whenever beta is sufficiently large, this Gibbs measure puts almost all of the weight on the ground states. So of course we have these two extremes, uniform measure and a completely concentrated measure. Independent spins, and remember the ground states, all the spins are dependent. They all have to be the same. So somewhere in between these two extremes, there has to be a change. And we call that change the phase transition. And one of the main ideas of statistical mechanics is to figure out where this phase transition happens. There's some beta C, a critical temperature, at which this change happens from the independence to the complete dependence. And then, moreover, we want to analyze exactly what happens at the phase transition. Usually physicists are most interested in the critical temperature, and interesting stuff happens there. And we can try to understand this mathematically. There are different quantities we can analyze at the critical temperature, especially something called the free energy, which I'll get to later. And in analyzing these quantities, we can say quite a bit about what happens at the phase transition, and then what happens above it and below it, too. Okay, so Gibbs measures are the main objects, and we look for this special beta critical temperature at which the Gibbs measure behavior changes dramatically. And now, going back to the Ising model, this is a picture in 2D. Of course, in 1D, it's the picture I showed you with all up spins or all down spins is very well understood. But even in 2D, we can say quite a bit. And so, Onsager was the one who described these are not ground states. Of course, you know the ground states are all blue or all red. Blue is spin up, red is spin down. But above the critical beta, so this is below the critical temperature, so for low temperature, the spins in the Ising model, they want to line up, but if you're not at zero temperature, they don't have to be completely lined up. So if you were at zero temperature, or beta equals infinity, you would see either all blue or all red. But when you're not at zero temperature, when you're below the critical temperature where things want to be magnetized, where things want to line up, but they aren't forced to be completely lined up, then you start to see these stripy patterns, like a Scottish tartan. So there is a precise description of what these stripes look like. They have to be at least width 2, it turns out. And there's a whole family of pictures that look like this, and they are what we call metastable states. So the ground states are the truly stable states. But states like this are sort of stable, and in fact, there's a technical term called metastable for them. Okay, so we know a lot about the Ising model. But Ising is just spin up or spin down. We want to be a little more realistic. We want to actually describe more realistically the behavior of real magnets. So in real magnets, you can kind of see the spins here in the directions that the magnetic filings are oriented. These spins are not just spin up or spin down, they're pointing any direction in free space. And so this is the motivation for looking at the Heisenberg model, where the spins can be on the sphere instead of just up or down. And there's a whole family of these models, of which Heisenberg is an example, and they're called n-vector models. So now, instead of just plus or minus 1 to the n, our spin configuration lives in an n-fold product of the capital N sphere. So little n is the number of our spins, and capital N is the dimension of the spin. And then we'll have a Hamiltonian energy similar to before. There's still a minus sign, and a sum. Now the sum is over all the neighbors. So you want spins next to each other to interact with each other, but spins far away don't interact. And then, instead of, before we just had the product of two spins, now we have the inner product, because these are higher dimensional spins. And you'll see that this specializes to the Ising model if you take capital N equals 1. It specializes to the XY model if you take capital N equals 2. That's where the spins are on the circle. And it specializes to the model I'm most interested in this talk, the Heisenberg model, when capital N is 3. So this is a general family of models. N equals 4 is called the toy model in physics. And n-vector models in general have been studied. So this is the general model. And now we want to focus on a particular kind of these general models because, well, physics is really challenging. And what we will often start with is what's called a mean field model or a mean field limit. And you can think of this as a really high dimensional model. High dimension for the lattice that the spins live on. Or the spins themselves, you want them to be a realistic dimension like 2 or 3. But the lattice that the spins live on, it helps, at least with the analysis, if you take it to be really high dimensional. And one way of doing this is by looking at the complete graph. K sub n, so a set of vertices and edges. The number of vertices is little n. And then our spin configuration, sigma, is a vector of these spins sigma I. Each spin sigma I lives in the n sphere, or n minus 1 sphere. And I've rewritten the Hamiltonian energy now, specialized to the complete graph. Still a negative sign, still a sum, but now this is a sum over all possible pairs of vertices because you've got a complete graph, so everything is adjacent to everything else. So the sum is over all pairs, and we have this 1 over 2n to scale things correctly because each of the inner products would be of order 1, and then if you're summing over n squared of such pairs, when you take limits, like I'll show you later, you want this whole energy to be of order n. So the 1 over 2n is a good scaling to take. And then we'll be taking n to infinity, taking the number of vertices in the complete graph to infinity. And this is, there's a correspondence with taking the dimension of a realistic lattice to infinity. Okay, so this is our mean field model. And we're most interested in capital N equals 3 for Heisenberg. And now mean field models are known to have a phase transition, a critical temperature, or beta, at which the behavior changes. And for instance, if you look at the Ising model, so all of these results at the top here are for the Ising model. This goes back to the 70s, the work of Ellis and Newman, and Dunlop and Newman, and then most recently Chatterjee and Shao, who brought a new technique to this model. And what they all show, basically, is that the critical beta is equal to 1. Below that beta, the average spin, so if you just average all of the spins, it goes to 0. And if you think about what this means, if the average spin is 0, that means all the spins are pointing any which direction. And if the spins are independent, then the law of large numbers, since the spins are just plus or minus 1, their mean is 0, and the law of large numbers tells you that the average spin will go to 0. Okay, so that corresponds to the independent case, the demagnetized case, and there's also a central limit theorem that can be proved there. Now, on the other hand, above the critical beta, if you look at the average spin, it's no longer going to 0 because now things are magnetized. Remember, large beta is low temperature. Low temperature things are magnetized. Spins want to be lined up. And so the average spin will be either positive or negative, but not 0. And you can show that there's a central limit theorem around either one of these polarized states, these magnetized states. And then, at the critical temperature, there's this funny limiting density, which is not Gaussian. It's e to the minus x to the 4th over 12, that describes the asymptotics of the average spin, right where things are changing from magnetized to not magnetized. And so this limiting density, this non-Gaussian density, is what physicists are especially interested in because it tells you a lot about the critical behavior of the model.
Can I just clarify something real quick? So you said that you have normal asymptotics around the two states.
Yeah.
Are those, you can think of those as random measures? So I mean, what do you mean by normal asymptotics around two states?
Okay, so just like there are two ground states, there will be two states, not plus or minus 1, but plus or minus m, and there's a formula for this m, where if you look at the average spin, it has a distribution, and that distribution has mean m, or minus m. And then things are normal around. And so you can see what's happening, like with your hand. So plus or minus 1, if things are independent, the average spin is 0 in the middle. Then at low temperature, there's going to be a directional preference, either up or down. And right at the critical temperature, things are going from 0 to one of the two possible preferences. And so it's right when they split. It's sort of like a bifurcation diagram where you have some quadratic potential and just one ground state, and then it goes through some transition, and then suddenly you have these two ground states. And it's in between, right where the one splits into two. That's what's happening at the critical temperature. And there's probability distributions for these average spins, and this funny non-Gaussian density tells you exactly how that looks.
Is there any political explanation why you pick up increment as the 4?
Why the 4th?
Yeah.
Well, sort of, I mean, you can think of it going through a cortex.
Okay.
That's a very rough definition.
There's no hysteresis whether you're coming from above or from below.
There's no hysteresis here. There is hysteresis in other situations, like if you throw in an external magnetic field. Then you see some very interesting things. Okay, and just for anybody who's interested, the hysteresis, you can imagine tilting this potential back and forth, and if you get enough of a tilt, things will go out, fall out of this state into this other state. So you can go back and forth, and there's like a leg in the state. Okay. Now, if we look at the general n-vector models, it has been known for some time that the critical beta is equal to capital N. That's where the phase transition happens. And below the critical beta, it has been known that the average spin decays to 0, like a law of large numbers. And this goes back to Preston and Schulman in '88. But the complete description, like for the Ising model, was not known. And so that's what we did. We provided a very complete description of this whole mean field Heisenberg model. So I've written the Hamiltonian energy again, this minus 1 over 2n, the sum over all possible pairs of spins of the inner product. And just as a summary of our results, we look at the average spin, 1 over n times the sum of the sigma i's. We show that not only are there laws of large numbers, those are fairly simple to prove. There are central limit theorems and large deviations principles. And this is for any temperature. Then we study the free energy, and we get our phase transition popping out at the appropriate value, 3. And we take a look at the average spin, actually the empirical distribution for the average spin, and we get central limit theorems away from the critical temperature and a non-central limit theorem at the critical temperature. And the critical limiting density has a funny form that I'll show you later. So this is an overview of our results. And then specifically, so at infinite temperature, beta equals 0, the spins are independent. And let's write P sub n to be the product measure on the n-fold product of the spheres. This is the same as the uniform measure. The easy results that were already known for a long time are that the average spin goes to 0. It's the law of large numbers, and there's a central limit theorem. Independence everywhere. So, in particular, this is also an easy consequence of the theory that these uniform random points on the sphere, they also have a large deviations principle. And what that means is if you look at the probability of this average spin being like a particular value x, this goes like e to the negative n I of x. And this I is called the rate function. And if I of x is 0, then this probability will be large. And if I of x is positive, this probability will decay exponentially. So zeros of the rate function I are very important. The zeros of the rate function will give you the macrostates.
So x is a point on the sphere.
X is a point on the sphere, or actually a point in R3.
Actually,
Because, yeah.
And the rate function?
I'm going to tell you what that is. It's obnoxious. We do not have an explicit formula for the rate function. We have an implicit formula for it. So it is some I of c, which is a sum of this function involving the hyperbolic cotangent, and a log of something over sinh. So you could, by hand kind of plot this rate function. It has a 0 at 0, and otherwise it's positive. And what that tells us is that the macrostates of the system, remember, independent spins, the macrostate is 0. The average spin is concentrated around 0. And this is recovering what we already knew intuitively, that at infinite temperature, the spins can point any direction. They interact with each other, but they're independent, and they're not magnetized, and this phase is called disorder. So this is our infinite temperature special case. Now, the power of large deviations is that there are several levels. We just did the most concrete level, and then there's the level on for empirical measures. And so this is also at infinite temperature. Now we look at the empirical measure of the spins, mu and sigma. So this is putting a delta mass at each of the spins. Of course, you can take this measure and find its center of mass, and that will be the average spin. So this level 2 specializes down to level 1, which we did on the previous couple of slides. but there will be some extra power to it. But so far, this large deviations principle follows from the theory very easily. It tells us that the probability that our empirical measure of spins is in a certain set B, and B is a Borel subset of the set of all measures, probability measures on the sphere, that this probability goes like e to the minus n times inf over B of, this is the relative entropy, h of mu is the relative entropy of mu, and mu is the reference measure, which is the uniform measure. And you look at the Radon-Nikodym derivative, and if that exists, then you form this integral for the relative entropy, otherwise it's infinity. And then, just like before, we had the only macrostate, the only zero of the rate function was 0. The analogous result here is that the only macrostate is the uniform measure. That says that the spins are uniformly distributed on the sphere. There's no preference for any particular direction. And if you average them, you get 0. Okay. Now the power of this theorem is that there is a result of Ellis-Haven and Turkington. This says once you have that kind of theorem for beta equals 0, you can push it to all positive beta. And there's a, I hesitate to use the word beautiful because it's actually pretty complicated. There's a complicated machinery for identifying certain things called hidden spaces and all this stuff. And now, so what we get, instead of these uniform measures Pn that we had before, now this is the measure that depends on temperature, beta. And the natural thing is the Gibbs measure. The partition function, I've written out explicitly. And then, all of the LDP at beta equals 0 extends to this whole family of LDPs at all beta positive. And they tell you that the Gibbs measure, so these are the states you're most likely to see at a particular inverse temperature beta. They go like e to the negative n times the inf over this set B Borel subset again, times inf of I beta nu. And this I beta nu, it's sort of like a rate function, and it's also like the relative entropy, because it has the relative entropy in it, and then it has some other stuff that comes from the Ellis-Haven-Turkington machinery. So minus beta over 2 times, and this is the center of mass of the measure mu, quantity squared, and then minus 5 beta. And 5 beta is just to make sure that there is no more than one, to make sure that the minimum of this thing is 0. It's just a vertical shift, but this vertical shift, phi beta, is called the free energy, and it has a lot of information in it. And then if we want to know about the macrostates, we will look to see where I beta is 0. So this free energy is also obnoxious, and I apologize for these complicated formulas. You can stop paying attention for a moment, and I'll just say, so the first definition here is the old-fashioned definition. The second part is the Ellis-Haven-Turkington machinery, and we used the machinery to figure out that the free energy is identically 0 below the phase transition, and then it's some complicated function, again, not explicit, but implicit, phi beta of gamma inverse of beta. And so, roughly speaking, it looks like this. So, beta equals 3 is the critical inverse temperature. It's 0, like so, and then it's some increasing function after that. And this is just very roughly what the free energy looks like. Okay, so now the phase transition comes from studying what happens with this free energy at beta equals 3. And it turns out that phi is continuous there, and its derivative is continuous. So this is what's called a second-order phase transition in physics, also known as a continuous phase transition. And to summarize what we've learned so far, below the critical beta in this regime, all the macrostates are zero. Everything is independent, and the average spin is zero. Then above this critical beta, things get interesting. And we have a complete description of these macrostates. They're basically, at the critical temperature, there emerges a preferred direction. And at first, this preferred direction is only slightly preferred. And it's preferred in this exponential form, but of course it could be uniformly any direction on the sphere. But once you have a particular preferred direction picked, then if you increase beta to infinity, remember this is going to zero temperature, then that preferred direction becomes stronger and stronger until at infinity you get a delta mass at that preferred direction, which says that all the spins want to be lined up in that direction. Okay, so this is a picture of the macrostates or the mean field Heisenberg world. And we have a definitive description of not only these large deviations principles, but also the central limit theorems. And so this Wn is a rescaled sum of the spins, and it's got the usual central limit theorem scaling, square root of n. And Wn goes to a standard normal random variable z. Now, really what we prove is this inequality, but that is equivalent, and I won't get into the technical details. So that's below the phase transition. We have a normal central limit theorem. Above the phase transition, there's also a central limit theorem with a different looking scaling and a non-standard Gaussian. Now, y is mean zero and the variance is complicated. I'll skip over why it's complicated. And then the really interesting part is what happens at the critical temperature. So there's a funny scaling. This is not a normal central limit theorem scaling. And we also look at the square magnitude of the spins, because this will wash out the preferred direction. Like, any direction on the sphere could have been preferred, and the old approach was that you had to condition on that preferred direction and then study the asymptotics around that direction. But we got around that by just taking the magnitude squared of the sum of the spins. So that washed out worrying about the preferred direction. And then the limit now is not a Gaussian random variable. It's a random variable with the following funny density. There's a normalizing constant, z, and then there's a t to the 1/2 times e to the negative 3ct squared. And because we've taken the magnitude squared, this is a density on the positive real line only. And this number c has a particular formula related to this constant, capital C. So we have this non-Gaussian limiting density at the critical temperature. That's describing the fluctuations of the average spin right at the transition from where there's no preferred direction to where there's a slightly preferred direction. And some of the key ideas, without going into details, well, I already mentioned the Ellis-Haven-Turkington method. And the really powerful method here is Stein's method, which has been experiencing a resurgence in probability. And so that's how we proved the central limit theorems and the non-central limit theorem. And if you know about Stein's method, one of the most popular ways of applying it is through the exchangeable pair. And we get an exchangeable pair from the Glauber dynamics, which is a natural physical dynamics. And then, so what do we want to do next? We want to study similar things for the XY model, and also to look at not just the statics. All of this story so far has been the statics of the Heisenberg model, but also the dynamics. So that's what my students are working on. I have 2 PhD students, one in math and one in physics. And the one in math is working on the mean field XY model, so that's when the spins are in the circle. And he's also looking at these higher n-vector models. And he's seeing some interesting things happening at criticality. This is a process of being proved. And my physics PhD student has been studying the dynamics for the mean field Heisenberg model. And ideally, what we would like to get there is some process level result, a version of Stein's method for the whole process of the dynamic spins. And other things I'm interested in along these lines are studying metastable states in the XY model. Well, really any of these models. Metastable states are fairly well understood in the Ising model, not so well understood in XY. And then, in line with this goal of going from microscopic to macroscopic, I've been talking with Jeremy Marzola and Donald Mattingly about how to go from the microscopic Heisenberg model to the macroscopic Landau-Lifshitz-Gilbert equation, which is an equation for magnetism. There are also some other challenges, like the 3D Heisenberg model. So I discussed the mean field Heisenberg model, which is like infinite dimensional Heisenberg model. But of course, the most interesting case would be 3 dimensions. That's where the lattice is 3-dimensional. The spins are also 3-dimensional. There are also interesting things that happen if you throw in some randomness in the couplings between spins, and those are called spin glasses. Of course, the Ising spin glass is the Kirkpatrick model, which is quite well understood now. And there are also quantum versions of these models, and I'm interested in all things quantum. So these are some things that would be nice to think about next. And then I'm going to skip over some of this physics inspiration and simulations for the XY model, and just end with a little advertisement. I'm organizing a semester at MSRI this fall on probability and PDE, interactions between the two fields, and especially applications to physics. So if any of you happen to be in Berkeley, please look us up. And so you can see from my talk that we've made some progress in understanding the physics rigorously of these magnetic models, and I didn't specifically mention it, but the XY model is the one for superconductors. Heisenberg is great for magnets, Ising is great for magnets, and XY is particularly good for understanding superconductors. And there are a lot of things left to try to understand about these models. And I'll stop there, and thank you for your attention.
Other questions?
Maybe, did any of your results surprise you?
Did any of our results surprise us? No, but my students' current results are surprising me right now. Because for the XY model at the critical temperature, he's getting a Gaussian critical limiting density, Gaussian, and I'm not sure I believe this.
So you should check it carefully.
And also another question. Did you consider other graphs than just complete graphs?
Other graphs besides complete graphs. The standard other graph that people consider is the nearest neighbor lattice. And there is, I understand, a rigorous way of understanding that dimension going to infinity, connecting it to the complete graph with the number of vertices going to infinity. But these nearest neighbor lattices are much more challenging to understand in the realistic dimensions. Except maybe on a line, they're fine. But 2 and 3 dimensions is pretty tough.
It produces boundary conditions that are really hard.
For instance, yeah, and if you, I mean, you can try to do periodic boundary conditions, and that might help, it might not, but yeah.
In any of the simulations, are you using something like the Gibbs sampler to try to
Yes.
understand the...
Yes, in fact, my physics student is using the Gibbs sampler to try to understand the dynamics of the Heisenberg model.
I was wondering, even when they originally did this, we were using it in image processing, and thinking of like the underlying image as a magnetic field that was imposing its will on another field, right?
Interesting.
Yeah, and so that in fact it all came from that intuition, and so I was wondering if you've done anything like that. So in other words, there's a base field, right? And then the charges are being their will is being imposed on another layer. Right.
So in this image processing application, you're thinking of like an external magnetic field?
Well, it was an actual image that you're trying to categorize the various regions.
Okay.
Okay, but actually their intuition came from magnetics. Yeah.
I'd
So
love to hear more about that.
yeah.
I had a question. When you ran through the Ising model, and you mentioned the limiting density exponential to the x4 term, does that correspond to the quartic coupling in the Landau-Ginsburg equation?
Okay, so the e to the minus x to the 4th over 12, does that correspond to the quartic coupling in Ginsburg-Landau? Maybe, I don't know. I haven't thought about that.
Anything else?
Have you come across the case that where the dynamics of the microscope was slower than the dynamics of the macroscopic, especially the phase transition?
Okay, so you're talking about different time scales of these dynamics.
Right. Some of those the phase transition is faster than the slow dynamics of the microscope. Because in a long time ago, I had this thing on the spoon glass. And they were trying to show that the neurons in the brain are slow, but collectively they can have a phase transition which is faster. So they got maybe this Ising model related to. So I'm wondering if there's any.
One thing I've observed along these lines are in simulations, if you have the temperature changing and this kind of Gibbs sampler going at the same time, it really depends heavily on how fast you change the temperature. Like if you, it's called like quenching. If you cool it off really quickly, you can get it to settle into one of the stable states, or maybe even a metastable state if you do things carefully. Or if you do this temperature lowering slowly, you see different behavior in the simulations. So there could be something interesting with this. Yeah, something like that.
Thank you.
Yeah.